Residual analysis implies we are observing information about the residuals that helps us to determine if we should trust our least squares regression line to model the association or relationship between the x and y variables. Primarily what we will do is look for three things regarding the residuals. First, do the residuals suggest a linear relationship? In our current case, yes. But look at the actual scatter plot and its corresponding residual plot. Clearly the data is not linear. Thus, a linear model, linear equation to predict y values from x values, would not be appropriate. A second thing we look for is consistency of variance. Look at this residual plot. Large scatter for smaller x values, but little scatter for large x values. This implies that the LSR line is good at predicting y values when x is large, but horrible for smaller x values. Thus, we would not trust our LSR line to predict for the entire domain of x values. The model is inappropriate in this case. We can see consistency of scatter in the flyer data, so its LSR line is trustworthy. But look at this residual plot. Inconsistent variance. A third component of residual analysis is to check for the normal distribution of the residuals. This one's kind of tricky. Now recall in prior videos how we discussed that no matter where we are in the x domain, the observed y values should be scattered according to a normal distribution, random scatter. Drawing a 1 standard deviation corridor on each side of the LSR line indicates that we should see roughly 68% of our data points in here. Translating this understanding to the residual plot, we should likewise see 68% of our residuals in that same 1 standard deviation corridor. Moving 2 standard deviations on either side would trap roughly 95% of the points on the scatter plot and thus their corresponding residuals on the residual plot. Here's an example of a residual plot that has a strange absence of residuals closer to 0. We're not seeing 68% within 1 standard deviation. We see instead 2 clusters of residuals with a gap in between. This corresponds to a scatter plot that might look like this. Suppose this is for patients suffering from back pain and how the new pain reliever is doing with regard to alleviating the pain. Notice 2 clusters with a large gap. Recall that random fluctuation follows a normal distribution. Thus, these differences are not attributed to random chance. Usually what we are looking at is 2 distinct populations that were combined into one. In this case, the upper cluster are severe sufferers of back pain. The lower cluster is for people with much lower levels of pain. What we should do once we identify the 2 populations is to calculate 1 regression line for severe back pain sufferers and 1 for lesser back pain sufferers. Another way to check the normality assumption is to look at a frequency distribution of residuals not tied to their x values. This means that we will take from this ordered pair only the y-coordinate, the residual of -19.5, and construct a dot plot of just it and the other residual values. Or we could make a histogram of them. We see a bell shape, thus we support the notion that the data is normally distributed about the prediction line. So residual analysis looks to confirm 3 things in order for us to trust our LSR line as a prediction model: linearity of the data, consistency of variance of the residuals, and normality of the residuals. Bottom line, if you see a noticeable pattern, something's not right. Don't trust the regression line. If we see random scatter with no noticeable pattern, that supports the line as a prediction model. If this were the case on an AP free response question for which we need to do residual analysis, here's all we need to say. There's no noticeable pattern, therefore the data is fine with regard to linearity, consistency of variance, and normality.